Hi, I'm Eric Herman. I'm an optical design engineer at Zygo Electro-Optics in Irvine, California. I'm going to be talking today about creating an ISO 10110 drawing. Working on standards is something I'm passionate about, and I've been actively involved in this community for about 5 years. I've been highly involved in trying to shape some of the international standards for optics that I'll be talking about today. Before we get started, if you have any questions during this presentation, please ask them in the chat window. We will try to address these questions either in the chat throughout or at the end of the presentation. If we run out of time before we answer your questions, we'll follow up with you afterwards. Additionally, as ISO 10110 can be a complex topic to understand, I've summarized a lot of the material covered today into a downloadable poster. It can be found in the handout section of this webinar or on the Zygo website. Lastly, after this webinar, there will be a brief survey. A link to the survey will also be sent in a follow-up email you should receive tomorrow. The motivation behind this webinar is to introduce people to the ISO 10110 drawing format and explain the coded notation it utilizes. There are many different ISO standards for optics. The technical committee solely responsible for optics is TC 172. The optics drawing standard, ISO 10110, is one series within this technical committee. There are many other standards within this technical committee. A subset of other standards TC 172 is responsible for are shown here. These standards each have their own tie-in to the ISO 10110 series. The backbone behind ISO 10110 is a coded system for specifying each of the tolerances for an optical component or system. By having the coded notation, the back and forth between engineers and fabricators can be minimized. As ISO 10110 is an international standard, the coded notation that goes across language barriers and allows a global vendor base. Breaking down an ISO 10110 drawing can effectively be done in three different areas. The drawing field up top is where the view of the optical component or system is shown along with any dimensions or tolerances. The middle field shown is a table field. The table field is a way to neatly provide information for each optical surface or component with minimal confusion. The table field should be read from left to right through the optical component, with the surfaces sandwiching the material properties. It isn't necessary to include the table field, but it is highly encouraged. In the instance that the table field is not included, the dimensions and coded information would be listed on the drawing field. These would be pointing at the respective surface or component. Lastly, the title field is at the bottom of the drawing. The title field is more commonly called a title block. The title field of an optical drawing is where the primary information needed is shown. There is some information that is necessary to include on an ISO 10110 drawing. The first of which is a statement letting the fabricator know that this drawing is following ISO 10110. The next information that is necessary to state is the wavelength to be used when interpreting the drawing. Previously, a default wavelength was in place for ISO 10110 drawings, but that standard has since been withdrawn. Stating the wavelength in the title field does not mean that the entire drawing must follow that wavelength. In certain specifications, it may be better to define other wavelengths along with their respective tolerance. The default unit for dimensional information is in millimeters. The temperature is assumed to be 20 C. Other units may be assumed, but they must be stated. Classically, a title block will contain a set of default or block tolerances that should be followed if no tolerance is listed. For ISO 10110, a separate part of the series, Part 11, lists each of these default tolerances. They are based on the diameter of the optical component and are extremely loose relative to manufacturing capabilities. On the right, is an overview of the coded notation that ISO 10110 uses, along with the associated subsection. Going through this list, the first three tolerance types, 0/, 1/, and 2/, are for material information. These tolerances are for the finished optical component and not the raw material. The 3/ is surface form or figure. This is the section that Zygo specializes in. The 4/ is used for centering or wedge of the optical component. The 5/ is for surface imperfections or scratch and dig. The 6/ is used for specifying the laser damage threshold. Preceding the tolerance by either a 0 or a 1 can change the level at which a tolerance should be applied. A preceding 0 looks at raw material tolerances, and a preceding 1 looks at system level tolerances. The listing of 13/ is for a system level tolerance. In this case, the transmitted wavefront is considered a figure tolerance that is applied for the entire optical element or system. The surface texture for an optical component will be specified using the mechanical surface texture symbol. Coatings for an optical surface are described with a lambda symbol within a circle. If you are trying to ensure that there is no tolerance, a dash should be listed following the respective coded notation. Jumping into an ISO 10110 drawing, dimensional information is conveyed either in the drawing field or the table field. There is no special coded designation for calling out dimensional information. The only additional dimensional information necessary is stating the radius of curvature of a surface with a preceding R along with the concavity of the surface. This assumes that the surface is spherical. This is to ensure that there is not a sign error for the radius value. The tolerances for a radii, if being done dimensionally, should be listed along with the value itself. When looking at the optical material, the first piece of information necessary is the material or glass for the optical component. This can be listed as either the glass manufacturer and name, refractive index and Abbe number, or the International Glass Code. Assuming the glass type is listed, it isn't necessary to list only one supplier. Associated with the 0/ is the stress birefringence. There is no code or class used for this tolerance. The stress should be listed as the allowable path difference in terms of nanometers per centimeter. For the drawing shown on the right, there is a stress birefringence of 10 nanometers per centimeter. The 1/ is for the bubbles and inclusions. Stating the bubbles and inclusions is done with the number of allowed bubbles or inclusions and their allowable grade. The grade for a bubble or inclusion is related to the square root of the bubble area. On this drawing, 5 bubbles or inclusions of a grade 0.25 are allowed. The last types of material properties are for the homogeneity and stria. Both of these tolerances are listed with the 2/ and use a class system for their specification. The homogeneity is listed first with a class indicator of NH. The value following is then the amount of homogeneity of the refractive index in units of parts per million. If we were to look at this from the shot designation, the example shown would be considered an H1 glass. The stria is similar in that it uses a class indicator SW. The value that follows is the maximum wavefront deviation over a 50 millimeter path in units of nanometers. Typically, the numerical class for stria will be listed by the glass manufacturer. As previously stated, specifying the raw optical material may be necessary for a fabricator when communicating directly with a glass vendor. In that instance, the numeric codes for ISO 10110 are preceded by an extra 0. Similar to the class system used for homogeneity and stria, a class system is available when specifying raw glass for the stress birefringence and the bubbles and inclusions. More information on specifying raw materials and their notation is in ISO 12123 and won't be covered today. Specifying the raw optical materials may still be done using the coded notation from ISO 10110 instead of the class system in ISO 12123. Looking at the surface form or figure can be done in many different ways. The general method of specifying surface form or figure is with the notation shown here. In that case, we can specify the power, irregularity, rotationally invariant irregularity, and the test wavelength. When using MX, it's possible to get the general notation for surface figure. If using MX, go to the ISO 10110-5 tab and select each of the properties for this notation on the right as shown. The information checked is then shown on the following line using the ISO 10110-5 notation. If we look at another form of the notation for surface figure, we can specify a surface with three different types of RMS quantifiers. These can be done in addition to power and irregularity that was previously shown. The RMS quantifiers are for either the total RMS deviation with the tilt removed, the RMS deviation with power and tilt removed, and the asymmetric RMS deviation, which is typically used for an aspheric surface. This notation is also included in the ISO 10110-5 tab in MX. Specifying the surface figure as a slope can be done as either the peak to valley slope or the RMS slope. The notation needed here will include the number of directions to consider, either one or two, and the orientation of the slope, either Cartesian coordinates or polar coordinates. Both of these parameters would be listed as subscripts following the initial callout for slope deviation. If neither of these are listed, the slope is assumed to be in all directions. The maximum slope deviation, the sampling length, and the sampling interval are then shown. In the example shown here, we did not specify the number of directions to consider, so all directions are assumed. This surface then has an RMS slope tolerance of 0.1 milliradians in all directions. The sampling length for one dimension is 1 millimeter, and the spatial sampling interval is 0.1 millimeter. Along with the slope tolerance is a surface power and irregularity tolerance. In ISO 10110, you can also specify a surface figure tolerance by Zernike terms. This can be done specifying the individual Zernike term tolerance as shown here, or a summation of multiple Zernike terms. When specifying the Zernike terms, you need to list both the N and M quantifiers for the Zernikes. This is to make sure you are keeping your notation consistent with the ISO 10110 standard. The notation that is used for Zernike terms in ISO 10110 is similar to the fringe Zernike notation. A more detailed explanation of the N and M terms is listed in ISO 14999-4. You are able to pull information about the Zernikes out of MX by looking at the Zernikes tab. In there, you can look at each individual term. As we stated in the beginning, a system level tolerance is preceded by a 1. The coded notation of 13/ is used when looking at transmitted wavefront. The same notation for figure tolerances that were used for surfaces can also be used for transmitted wavefront. When looking at the transmitted wavefront, additional information is needed for the transmitted wavefront specification. You must list the pupil position, pupil diameter, and object or image point to be used in the testing condition along with the specified tolerance. This information is necessary for metrology conditions. The output information for transmitted wavefront is shown in MX in the standard interferogram view rather than a separate tab. Since there is a lot of information here, do we have any quick questions that we can cover?
Hi, Eric. We did get a couple questions in, so I'll go over those now. There was a little bit of confusion over the class indicators for raw materials versus finished parts. So why can't we just use ISO 10110 for all of it?
So we can use ISO 10110 for all of the indicators of raw materials, but they don't go the other way. So you can use ISO 10110 notation for a raw material, but you can't use ISO 12123 notation for a finished optical component.
Okay, that's hopefully helpful. The other one that I got here is about units. So you talked about surface figure tolerance and mentioned that you can't use waves or that it's like default in millimeters. What units do you typically use for surface figure tolerance?
So for surface figure, the default units are in terms of fringes. You are not allowed to list surfaces in terms of waves, but you can also list them surface irregularity as figure tolerances in linear units. When you get to transmitted wavefront, the default then becomes in waves, but you can also still list them in dimensional units.
Okay, thanks. I have one more quick question. Is the PowerPoint going to be available for download somewhere afterwards?
It it should be. We'll have to take a look at that, but again, a lot of the information that I'm covering here is in that poster, and I would highly encourage you to look at that.
For anyone who hasn't found it, that can be found on the handouts section of this webinar. We'll look into, as Eric said, it should be available in PowerPoint form. If not, this entire webinar will definitely be posted on our website where you can refer to it again.
Okay, moving on, the surface texture is shown on a drawing with the mechanical surface texture symbol rather than a coded notation. The surface texture is specified as either a polished or ground surface over a stated spatial band. These spatial bands will typically be used for a surface roughness or waviness range. There are multiple methods for specifying the surface texture. A selection are for the surface roughness, waviness, areal roughness, slope, and power spectral density. Additionally, it is possible to specify a surface roughness with a grade system. This notation has a default spatial band of 2 microns to 1 millimeter. These would be stated as a P1 through P4 grade with the surface roughness specification from 80 angstroms down to 10 angstroms. When we look at surface imperfections or surface quality, there are 2 methods of specifying an optical surface. This can be done with either a dimensional method or a visual method. The dimensional method of surface imperfections are shown here. This notation will have a defined quantity of imperfections and the grade of an imperfection. With the dimensional method of surface imperfections, they are different types of qualifiers that can be used. The general notation without any qualifiers are for imperfections of the final part. The next are imperfections that relate directly to optical coatings. Specifying surface imperfections for coatings is not necessary. If the notation is included, the general notation will then be used for the optical component prior to the coating process, and the coating qualifier for the final component. You may also have long imperfections on a surface. The qualifier of the L means that the grade of an imperfection is greater than 2 millimeters long. The last type of surface imperfections noted here are edge chips. These are specified with the preceding E. The value is the depth into the optical part from the edge that chips are allowed. If we continue to look at surface imperfections, we can also use the visibility method, which is similar to the classic MIL scratch and dig method. This type of method is comparative, where the inspector will look at a reference comparison and analyze the surface quality. The notation for the visibility method on an ISO 10110 drawing is noted the same way you would see a scratch and dig callout. The addition of edge chips similar to the notation in the dimensional method is allowed. As an important note, it's necessary to state the make and model of the comparison standard that you will use. This is to ensure that both the fabricator and the end customer are in an understanding of the standard to reference the surface imperfection against. Switching gears, when we look at optical coating surfaces, the coded notation is different from other tolerances on an ISO 10110 drawing. Coatings are specified for a surface with a lambda in a circle, followed by the type of coating. Different from other types of notation or parameters for an optical component, the lack of a lambda in a circle does not imply a default tolerance, thus no need for a dash. One thing that is key to the requirements for coatings is listing the type of coating, i.e. AR for anti-reflective, along with the design parameters. This is to mitigate confusion in the application that the coating will be used. Specifying a coating is done with 3 different parameters: transmission, reflection, or absorption. Along with these parameters, the notation of the coating can be specified in 4 different ways, either unpolarized or polarized, and for an absolute or average term. If a coating being specified on an ISO 10110 drawing appears confusing based on the description, it's possible to also specify the coating graphically. In that case, a coating curve may be provided with the wavelengths and their coating parameters shown. When dealing with a graphical representation of the coating, explicit callouts for the wavelengths and their transmission or reflection should be shown with arrows pointing towards the upper and lower bound. In the case of specifying a coating as per the graphical method, you are only allowed to use absolute value limits, not averages. Along with specifying the coating itself, in many cases, the environmental durability specifications for coatings may be necessary. The notation for those requirements are outside of the ISO 10110 purview, but covered in another ISO standard within TC 172. The ISO 9211 series is explicitly for coatings and their different properties. For environmental durability, those requirements are shown in ISO 9211-3. In that standard, the basic notation is described for all coating-specific environmental or durability tests. The notation used by this standard is shown here. The standard number is listed and subsequently what type of test and the severity level of said test. The tests that are explicitly for coatings, such as adhesion and abrasion, are described in ISO 9211-4. All of the environmental tests are described in the ISO 9022 environmental testing series. To better explain this notation, we have an example where we are setting the requirements for abrasion. We are referencing the standard used, ISO 9211-4, the type of test to be performed, abrasion, and the severity level of this test. One of the key parameters when specifying an optical element is the centering or wedge tolerance. This is done with the / notation. There are many different types of quantifiers that can be used to specify the centering. When looking at these different parameters, we can look at surface tilts or runouts. If we are looking at an aspheric surface or freeform surface, it will be necessary to include the surface decenter along with the tilts. Specifying the centering for an optic can be done either explicitly with the datum notation or implicitly. Using a datum may be critical when referencing the centering tolerances, but not in all cases. Going over a couple different methods of centering, first we show the centering for the tilt of a single surface relative to the other optical surface. In this case, we're looking at the datum on one optical surface and the edge at which that optical surface meets the cylindrical surface or outer diameter. The second example is shown when specifying the tilt of both optical surfaces relative to the cylindrical surface or outer diameter. In this case, each side will have a tilt tolerance or a runout. It is possible to specify the centering tolerance for the entire optical component with a beam deviation tolerance. In this instance, the cylindrical surface or outer diameter is the reference datum. Note that the coded notation is for the entire optical element, and that is done with the 14/. Lastly, if looking at a doublet, the centering tolerances are similar to the single surface tolerances. In this example, the left optical surface and the edge at which that surface meets the outer diameter are the two datum. The right optical surface for this first lens then has a tilt tolerance. The second optical element will have a centering tolerance relative to the first by using the notation of a delta tilt. Lastly, the right surface of the right optical element will have a tilt tolerance relative to our datum. If we're looking at an aspheric optical element, a separate part of ISO 10110 is used, part 12. It will be necessary to state which optical surface is aspheric by replacing the R notation on the surface with an ASPH. For these types of surfaces, we will not state the concavity as the coordinate system and aspheric terms provide that concavity. It is necessary to then include all of the aspheric terms for this surface and the equation used. Lastly, a table showing the surface sag or slope is required. This is used as a verification method for the aspheric terms of the surface. When looking at a general or freeform surface, a similar method of notation to the aspheric surface is used. This is noted in ISO 10110-19. In this case, the surface is specified with a GS. What becomes key with a freeform optical element is the coordinate system used to define each surface. In this example, we are showing the global origin of the component and then the local origin for the optical surface itself. Assuming the table field is used, listing the global or local coordinates on an ISO 10110 drawing will be done in the heading for each surface. Wrapping up, ISO 10110 uses a coded notation for defining an optical element. This coded notation is key to the power of ISO 10110. Zygo's MX software has implemented some of the coded notation used in ISO 10110. This is to simplify complexity for users in checking their surface figure or form against the stated tolerances. As a note, these standards are constantly evolving through global input in TC 172. These changes are being done to better serve the optical community. A recent example is the creation of a separate standard for freeform surfaces, ISO 10110 Part 19. Most of the information covered here today is available as a downloadable poster, which you can find in the handout section, as I stated, as well as it'll be on the Zygo website at the link shown. Lastly, there will be a detailed book covering all of this information and a whole lot more coming out later this year titled Modern Optics Drawings, the ISO 10110 Companion. Do we have any other questions?
Hi, Eric. We do have a couple more questions. So we had one on scratch dig. Why do we need to put a comparison standard on the drawing? Can't we just say like 60/40 scratch dig like we would traditionally?
So you could, but you also want to tell the fabricator what you're going to look at so that you can make that comparison. So if you're using one comparison standard, it might be slightly different than another. And so you can write on your drawing, whatever your comparison standard is or equivalent, and that's just to let the fabricator know, this is how I'm going to look at the end part.
Okay. And then one more question. Why do we need to state the standard as part of the coding testing? Isn't it all one standard for coding durability?
So for coatings themselves, in the durability ones are all in the ISO 9211-4, but because of the environmentals, there are a lot of different subsections. I think there's at least 10, it's between 10 and 15 different standards for all environmental tests. And so for each one of those, it's a different part. So for example, you would use the test for temperature for one section, and then for salt mist for a different section of that ISO 9022 series. So you want to list what that standard is just so that you can make sure that the test is being done properly.
Sounds good. Sounds like the moral of all of this story is it's always better to give more information on your drawing than less.
Yes.
All right, that's all of the questions I've had come in. Certainly, if additional questions come in further, we can answer them offline after the presentation.